To part 4 of chapter 3. Today we are going to talk about types of chemical equations as well as how to balance those chemical equations. So a chemical equation is a way of writing a reaction, and reactions involve chemical changes in matter resulting in new substances. So if you'll recall, the law of conservation of matter says that matter can't be created or destroyed. So these reactions just involve the rearrangement of the atoms. And so they might, exchange them or combine them, right? But we'll be producing new molecules. The way that we write these reactions is that our reactants will go on the left and the products will go on the right. And then we have an arrow in between showing the direction of the reaction. In this class, our reactions are always going to go from left to right. If you get into higher levels of chem, you may see arrows that go backwards or arrows that go both ways. But in this class, we're just going to have our reactions going to the right. So our reactants will always be on the left, the products will be on the right. Here we have, carbon plus oxygen gives us carbon dioxide. So our reactants are carbon and oxygen, and our products are carbon dioxide. You will also have the states of matter of the reactants and the products. G stands for gas, L stands for liquid, and usually we'll write this as a cursive L. S stands for solid, and AQ stands for aqueous, which means dissolved in water. And we are always going to put our states of matter after our chemicals. So like carbon here is a solid, oxygen is a gas, and carbon dioxide is a gas. You'll notice that O2, right, because oxygen is by itself, and oxygen is a member of Hofbrinkel, which we talked about in an earlier lecture, and that tells us all of the diatomic molecules. So carbon can sit by itself because it is not a member of Hofbrinkel, but oxygen, anytime it's by itself, we'll write it as O2 because it is a member of Hofbrinkel. And so these are all of the diatomic elements. And then back to AQ, that's dissolved in water. So most things when we see them, if it looks like a liquid, like in lab, if it looks like a liquid, it's probably not a liquid. Our pure liquids are going to be things like mercury and bromine, and sometimes we'll have pure water. But most times if you see a liquid, it's actually going to be an aqueous solution. So like if you saw some salt water, that would be an aqueous solution of sodium chloride, right? Which sounds a lot fancier than salt water. But it's not a liquid, it's an aqueous solution because a solid has been dissolved in water. So make sure you keep an eye on that. So we have 5 types of chemical reactions. The first one is a combination reaction. It's also sometimes called a synthesis reaction. We also have decomposition reactions, single and double displacement reactions, and sometimes you'll see this written as single and double replacement reactions. That means the same thing. And then combustion reactions, which we talked about a little bit in an earlier lecture. So I'm going to go over all of these. The first one is combination or synthesis reactions. And in combination reactions, we have 2 reactants that are combining to give a single product. So that's A plus B gives AB, right? So these 2 things are combining together to make one thing. And it doesn't matter if A and B are elements or if they are compounds. All it matters is you start with stuff that's separate and you end with them bonded together, okay? So like in this first example, we have 2 elements, right, sodium and chlorine, that are bonding together to make a compound. And we're always going to end up with a compound on the right-hand side. Here, we have 2 different compounds, or 2 different molecules, right, that are forming together to make a compound. But again, it's just 2 things coming together to make one thing. Same thing here, we have 2 elements that are reacting together to make one compound. So for all of these, we have 2 things combining to make one thing. Decomposition reactions are exactly the opposite. We have one thing, right? One compound, one molecule breaking down into 2 or more pieces. So like here we have lead oxide, which is breaking down into a different form of lead oxide, and oxygen gas. All right, and so for all of these, we have one thing that's breaking down into 2. It could also break into 3 pieces, but it just needs to be one thing breaking down into 2 or more pieces. You'll see this triangle here which you may not be familiar with, but anytime we have a triangle over the arrow, that means that the reaction is being heated. So this is a heated decomposition. So what happened is we put this lead 4 oxide and probably into like a crucible or something, and we heated it up, and that caused the decomposition into lead 2 oxide and oxygen gas. So this caused some of the oxygen to be released during the reaction. But all that triangle means is that we've heated it. Single displacement reactions is when we have an element reacting with a compound, and that element is going to replace one of the elements in the compound. And this is going to be easier when we actually see it. So like if we have A and reacting with a compound, so an element reacting with a compound, this element is going to swap out and essentially kick out that B. So now A ends up bonded to C, and B is left by itself. So if A is a metal, then it will kick out the other metal. If A is a non-metal, it will kick out the non-metal. So it could kick out C, right? So we could also have ended up, so this would be like, if this was a metal, this would be how this ends up. If A was a non-metal, then we would end up like, we would end up with this. If A was a non-metal. Okay? So it's just going to kick out whichever one it is. So our example here is that zinc is reacting with HCl. And HCl, in this, hydrogen is kind of acting like a metal, because you can think hydrogen forms H+, right? And zinc forms zinc 2+. So zinc will kick out the hydrogen. So zinc will switch out with the hydrogen, which causes hydrogen to be by itself. And now zinc is being bonded to the chlorine. And again, remember Hofbrinkel, right? So when zinc is by itself, zinc can sit without a 2, but when hydrogen is by itself, hydrogen is a member of Hofbrinkel, so it needs this 2 after it because it's diatomic. So just be careful there. You're always going to follow these bonding rules, right? So like when we figure out that zinc needs to be bonded with chlorine, we know zinc is a 2+, and chlorine is a 1-, so that's how we're ending up with ZnCl2. Okay, so always follow these bonding rules when you're predicting products of these reactions. In a double displacement reaction, we have 2 compounds that are switching partners. Okay, so instead of having AB plus CD, we're going to think of, you can either think of the metals switching or of the non-metal switching. Here, the non-metals have switched, and so A will end up bonded with D, and C will end up bonded with B. But again, you could have written it as the metal switching, right? It'll end up with the same products. But essentially, we have 2 compounds, and they are switching partners, and they yield 2 new compounds. We're going to spend a lot of time on double displacement reactions, especially when we get into net ionic equations. So when we're looking to see if a double displacement reaction has occurred, we're going to look for things that are characteristics of a chemical change. Heat evolution, formation of a precipitate, gas production, right? All of those would be evidence that we've seen a chemical reaction occur. Here, this is formation of a precipitate that's shown in this picture. And formation of a precipitate is just when you have 2 clear liquids. And by clear, I mean that you can see through them, not necessarily that they look like water, right? Like if you had a copper solution, it might be blue, but you could still see through it. And so when we have these 2 clear solutions and we pour them together and you're getting something that happens, right? This is making a yellow product. And eventually, if we let this sit long enough, it will make a yellow powder that sits on the bottom. And that would be our precipitate. Our precipitate is a solid that's going to form on the bottom of our solution. So, and we're going to spend, like I said, we're going to spend a lot of time on this. So typically when we do a double displacement reaction, one of them will end up being a solid, and the other will end up staying aqueous, which means it's dissolved. But in terms of writing the reaction, here we're going to have our nitrate and our iodine, right? Our 2 anions are going to switch places. So now iodine will end up bonded to our lead, and our nitrate will end up bonded to our potassium. And again, follow all of your bonding rules, right? Like potassium's a 1+ and nitrate's a 1-, so they completely cancel out and we get KNO3. Lead is going to be a 2+. based on this. This tells us that our lead is a 2+, and our iodine is a 1-, which means we're getting PbI2. Okay. Combustion reactions are always going to follow the same pattern. It's going to be a hydrocarbon reacting with oxygen gas to produce carbon dioxide and water. So here I have it written as kind of a general reaction. This fuel here is your hydrocarbon, and a hydrocarbon means something that's just made up of hydrogen and carbon. Sometimes it will have oxygen too, but it's going to have at least hydrogen and carbon. And then it's always going to react with O2 to form carbon dioxide and water every single time. And these are all going to be gases. This will typically be a liquid here. Not always, but a lot of times. So we're going to have something reacts with oxygen gas to produce carbon dioxide gas and water vapor. Whatever this hydrocarbon is at the beginning, will dictate what all of these coefficients are because we're going to have to balance the equation. But everything else remains the same. The only thing that's going to change is this and the coefficients. Otherwise, it's always reacting with oxygen gas to form carbon dioxide and water. So those coefficients that I was just talking about are numbers that are placed in the front of reactants and products to show the ratio in which they combine or form. This allows us to obey the law of conservation of matter, because if we look here, right, we have 1 carbon and 2 oxygens, and we have 1 carbon and 2 oxygens. So that means that this is balanced because we have the same number of carbons on each side and we have the same number of oxygens on each side. But if they were different, then we would need to put coefficients, right, numbers in the front to allow us to balance this chemical reaction so that we obey the law of conservation of matter and we're not causing matter to be created or destroyed during our reaction. We're never going to write the coefficient 1. We don't write 1s in chemistry. If something exists on your paper, that means that there is an imaginary 1. But we're going to write all of the other numbers. So if we're looking at this on a small scale, 1 atom of carbon is reacting with 1 molecule of O2 to form 1 molecule of CO2. But on a large scale, we can think of these as being mole ratios. 1 mole of carbon reacts with 1 mole of O2 to form 1 mole of CO2, which is usually more what we're going to use it for as we move forward. So, like I said, since no atoms can be gained or lost during a chemical reaction, we have to balance it. And if we look at this, right, say that these 2s weren't there. We would have 1 carbon, 1 carbon. We would have 2 oxygens and 1 plus 2, which would give us 3 oxygens on that side. So that means it's not balanced. We also have 4 hydrogens and only 2 hydrogens here. So again, it wouldn't be balanced. So instead, we add in these coefficients so that we check and make sure that there are the same number of atoms on each side of the reaction. So with the coefficients, right, we have 1 carbon, 1 carbon. And for the hydrogens, we have 4, and then we have 2 times 2, which gets us 4 hydrogens. And then oxygens, we have 2 times 2, which gives us 4 oxygens on that side. 2 times 1 plus another 2 gives us a total of 4 oxygens on that side. So this reaction is balanced because we have the coefficients. So anytime you write a chemical reaction, you're always going to need to include the reactants and the products, the arrows, the states of matter, which are like the gases and liquids and things like that, and it must be balanced. If you ever write a chemical equation and it is not balanced, your equation is wrong because you have to write it balanced. Otherwise, you are disobeying the law of conservation of matter. You're just creating and destroying things out of nowhere. So in order to balance them, you're going to add coefficients until you get the equal number on each side, right? An equal number of atoms on each side. This is really important. Never, ever, ever change the subscripts of a formula. Okay, and so what I like to say is if we think of H2O, right? H2O, that's water. You drink it and you're happy, right? Yay, water, you need water to survive. But if you think about H2O2, right, that is hydrogen peroxide. And that one, if you drink it, you're not going to feel so well. You drink enough of it, you're not going to make it. Okay, so I like to say that subscripts save lives, right? H2O, good to drink. H2O2, not good. So never, ever, ever change the subscripts of a formula because you're changing the chemical compound. The only thing you can do is change the numbers in the front. You can only change the coefficients. And so I like to balance them like when you're getting used to it. If you're great at balancing equations, then you just go for it. Balance them however you want. If you're not great at balancing reactions, you can send me an email and I will send you a link to a simulation that can help you out. But you can also just follow this kind of way to do it. So I like to say, okay, on this side we have nitrogen and oxygen. On this side we have nitrogen and oxygen. I have 1 nitrogen, 1 oxygen on this side. I have 2 plus 1, which gives me 3 oxygens on this side. And right now I have 1 plus 2, which gives us 3 nitrogens and 3 oxygens on this side. So we have 3 of each of those. We're going to add coefficients so that we make these equal, because right now they're not equal, it's unbalanced. But if we toss a 3 out front here, now I have 3 nitrogens and I have 3 oxygens. And so by doing that, now I have balanced my chemical equation. I have 3 nitrogens on each side and I have 3 oxygens on each side. Okay, and so that's kind of the process that I would do. Count how many you have on each side, add coefficients, change these atom counts until you get equal numbers on each side. And then once you get good at balancing reactions, you won't need to do that so much. So here's another example. We have, before we get there, if we look at this, we have aluminum, oxygen, and carbon. And we have aluminum, oxygen, and carbon on each side. And so I would go through and figure out how many you have of each. So we have 2 aluminums and 3 oxygens and 1 carbon on the left, and we have 1 aluminum and we have 2 oxygens and 1 carbon on the right. So we're not balanced. The only thing that's balanced is the carbons, but nothing else is balanced, so our reaction is not balanced. I would always start off with balancing the metals. Metals tend to be easier to balance first than the non-metals. So I would go metals and then non-metals after that, except for hydrogen and oxygen. I would do those kind of last. Okay, so here we go. In this one, I don't follow that, but in general, this is a really good way of balancing them. So let's go ahead and balance the aluminum. So if we balance our aluminum first, we toss a 2 in front of the aluminum here, right? That does 2 times 1. That gets us 2 aluminums on this side. So now our aluminums are balanced, our carbons are balanced. The only thing that's not balanced are our oxygens. So we're going to go through and try and balance our oxygens. We have 3 on the left and we have 2 on the right. And so if we're thinking about this, we need to find the lowest common multiple, essentially. If we have 3 on the left and 2 on the right, we can multiply something, each of those by something to get to 6. So I'm going to go ahead and do that. So I'm going to toss a 2 out front here. So 2 times 3 will give us 6, and 3 times 2 will give us 6, and that will balance our oxygens. So now we've got 6 oxygens on each side. But when we do that, we messed up other things, right? Now we've messed up our aluminum, so now we have 2 times 2, so we have 4 aluminums, but we only have 2 on the right. We've also messed up our carbons. We have 3 times 1, so we have 3 carbons on the right. So now the only thing that's balanced are our oxygens. So we need to go back and rebalance everything else, okay? So we can go ahead and balance our carbons. So if we put a 3 out here, that will send our carbons balanced. And so now we need to go and fix our aluminums. We have 4 on the left and 2 on the right. So instead of being a 2 here, right, we can make that a 4. And that will cause our aluminums to be balanced. So we go through and we check. Okay, now we have 4 aluminums on each side, right? 2 times 2, and we have 4 times 1. So our aluminums are balanced. And then, as far as the oxygen goes, we have 3 times 2, which gives us 6, 3 times 2, which gives us 6. And then our carbons, we have 3 times 1, which gives us 3, 3 times 1, which gives us 3. Everything is balanced, and now we have balanced our equation. And so this would be the correct form of our equation here. And you'll notice it also has the states of matter for all of them. Sometimes you may need to reduce coefficients of your balanced chemical equation. So if you get to a situation where you have, 4 and 2 and 4, and yes, it's balanced, right? We have 8 hydrogens on each side and we have 4 oxygens on each side, but our coefficients are not in their lowest common form. So we will reduce our coefficients, which means that we will divide them all by 2. So then we'll get 2 and 1 and 2 for our coefficients, and we still are balanced, right? We have 4 hydrogens on each side, 2 oxygens on each side. It's still balanced. You just need to make sure that you have reduced your coefficients so that you are in, that lowest common multiple. Here's our last example. This one has polyatomics, right? We have carbonate and we have hydroxide that is showing up. And you'll notice that we have carbonate stays together on each side and the hydroxide stays together on each side. So when you have these polyatomics that stay together, you can balance them like an element. You can balance like carbonate and hydroxide just like you'd balance the zinc and potassium. But you can only do this if they stayed together. If they break apart, right, like you only have carbonate on one side, then you would need to balance it as carbon and oxygen. But so if we're looking at this, right, we have zinc, we have carbonate, we have potassium, and we have hydroxide on both sides. Zinc, carbonate, potassium, hydroxide. We have 1, 1, 1, 1 on this side, and we have 1, 1, 2, 2 on this side. So if you'll notice, our potassium and our hydroxides are not balanced. So let's go ahead, if we balance our potassiums here by putting a 2 out front, that will cause us to have 2 potassiums, but also 2 hydroxides. And that will actually balance our equation just fine. Okay, but the whole point of this slide is to show you that you can balance the potassiums and the the carbonates and the hydroxides, those polyatomics, just like elements if they stayed together during the reaction. And this will oftentimes make your balancing a lot easier and a lot faster, because otherwise, if you were trying to count up all of these oxygens, right, that show up all over the place, it's just going to take you a little bit longer. And that's the end of this set of slides. So today we talked about our types of chemical reactions, a little bit about predicting our products, and how to balance chemical equations. So go ahead, practice this on your Chapter 3 lecture worksheet. And as always, if you have any questions, please send them to me. Talk to you next time.